sites from 100 terabytes of satellite imagery. And it's kind of like a two-part talk. The subtitle is Best Practices for Large-Scale Geospatial Cloud Workflows. So we'll try and sprinkle in some of that along the way. So let me move this over here. So as a quick roadmap before we dive in, I mentioned that there's going to be like two threads for this talk. So the first is going to be science. So it's about snowmelt timing and why it's important. This is reminiscent of my PhD work. So I'll be focusing on how I built a data set here and what it reveals about the different controls on snowmelt timing. And the second thread, which we'll kind of touch halfway through and kind of like dance between, is the engineering side of things. So this is how you'd actually go about processing one of these data sets that has like 100 terabytes of input data, and how to turn that into a globally consistent data set. So they motivate each other, and yeah, you'll see there'll be like a brief intermission about halfway through the science to talk about some of this stuff. Okay, first we're gonna talk about what is seasonal snow, and I'm really hoping this video plays. Oh, great. Okay, it does. So it starts in October, and as we enter the winter, the snow begins to advance across the northern hemispheres. So coming down towards the equator, and it covers nearly half of the northern hemisphere by February and March. And as snowmelt begins, snow cover retreats up to the poles and to the higher elevations. And while we're experiencing summer and we have the lowest amount of snow cover, the opposite is happening in the southern hemisphere. And seasonal snow is particularly important for us because it more than a sixth of the world's population relies on runoff from seasonal snow and glaciers for agricultural and domestic water supply. And seasonal snow acts as a natural water tower, which is basically just storing critical water resources while it's snowing. And then when the summertime comes and there's less water availability, you're able to get some water through the snowpack. And since we rely on seasonal snow for so many applications, including domestic water usage, as we show in this plot, here is specifically about the agricultural uses of water, snowmelt water. And if you look at where we live, kind of like a dark blue area, that's showing that there's greater reliance on water from snowmelt. And in California alone, more than 70% of the water in the San Joaquin River Valley comes from the snowpack in the Sierra Nevada. And this pattern, repeats globally in a lot of these hotspots, including high mountain Asia. So briefly, just looking at illustration of how snowmelt turns into streamflow. We have a mountain snowpack here, and river, and then going to an agricultural field. So we measure the amount of snow as snow water equivalent, what you'll see on that y-axis on the top plot. And basically, we'll just call it SWE throughout this talk. SWE is basically if you have like a snowpack and you just melt it all down and turns into water. So it's SWE, snow water equivalent. So here's a progression of a usual year. So as the snowpack accumulates throughout the winter, SWE increases, and then when melt begins, SWE decreases. And you can note the progression of water in the snowpack with the icons. So the darker blue, there's going to be more water in the snowpack. So once the snowpack has warmed and fully ripened, as we call it, any additional energy that into the snowpack will cause water to leave the snowpack. And this point in particular is called runoff onset. And that's basically when water starts just leaving the snowpack and entering our streams. So that's why it's a critical hydrologic parameter. And so, yeah, the dotted line there is runoff onset. And this can vary in different years. For example, this year, that we probably haven't gotten as much snow as we usually do. So this, sweep curve and stream flow curve might look different, a little bit lower and shifted towards the left, melt earlier. So understanding this timing is critical for downstream water availability. So that's what my work is going to be focused on and what I'll be talking about today. Snowmelt timing varies a lot, though, in space and time. It's not as simple as just a sweep curve that controls the globe. For a single mountain range, snowmelt timing can vary by months from low to high elevations. There can be 20 to 40-day differences in melt timing just between sun-facing and shaded slopes. And several months of difference between the mid-latitudes and polar latitudes. There's also large interannual variation for the same spot on the globe. So snowmelt timing can shift over a month, largely due to winter and spring, synoptic scale meteorology, so big like weather patterns. Things like high and low pressure areas, fronts, mid-latitude cyclones. But of particular importance for snowmelt timing is the advection of these like really warm, wet air masses that happens in late winter and early spring, and that accelerates melt. And to complicate things even further, these weather patterns also interact with the topography and these other factors. All in all, there's just a lot of spatial and temporal variability in snowmelt timing, which is why we want to observe it. In this plot here, we're just talking about how snowmelt timing is shifting earlier and earlier. So this is the Western US, and you're seeing that peak snowpack is occurring 8 days earlier since 1982. So the larger the pink marker here, the larger the trends towards earlier peak snowpack. And the current techniques that we use to measure snowmelt are quite limited. Right now, we use a lot of snow monitoring stations, but these are just, point scale automatic weather stations, in the mountains. And so you're really only measuring snowpack at one specific point. And there's other methods like remote sensing methods, what I work with. One of them is optical remote sensing. So just looking at like satellite imagery that you can see with your eyes. And unfortunately, clouds are very common during the melt season, so that makes it a little bit harder to use that. There's also passive microwave remote sensing. And I won't get into the details of this, but just know it has very coarse resolution. So you really can't get any sort of like fine scale spatial detail. So in this talk, we're going to be talking about C-band synthetic aperture radar, or C-band SAR. It's a type of active remote sensing that transmits and receives microwave pulses. The received pulses are called backscatter. So if you hear me talk about backscatter, we're just talking about this reflected signal. And it's backscatter for how is what we use to infer the physical properties of snow. So C-band refers to the specific wavelength of microwave radiation used, and it's this wavelength that will determine the properties that are advantageous for us to learn about. So for example, here's an optical image of Mount Rainier, clouds, can't really see what's going on. But in the C-band SAR image, taken at roughly the same time, we can see straight through the clouds. And that's really helpful for us to do these like long time series analysis without having clouds get in the way. It's not exactly measuring what your eyes can see, but it's powerful because you can use it day or night. And the main property that we're going to be leveraging here is that dry snow to C-band radar is essentially invisible. It'll go straight through, just like it did with the clouds, and bounce back, and there won't be that much like signal attenuation. Whereas with wet snow, you're going to have lower backscatter because the signal is going to be absorbed by the water in the snowpack. And the input data that we're going to be using today is C-band SAR data from the Sentinel-1 satellite. It's going to play. Oh, great, it does. So here's a little artist rendition of a Sentinel-1 satellite capturing some SAR imagery. And Sentinel-1 is a constellation of C-band SAR satellites in polar orbit. So they're going to be repeating and measuring at like the same time of day for every acquisition. And the spatial resolution is 10 to 20 meters, so it's very high spatial resolution and high temporal resolution with repeat overpasses every 6 days. And here we're just excited that there is an addition to the Sentinel-1 constellation because we had one of the satellites fail a couple years back. Okay, so returning to the illustration of the snow monitoring station. Now that we know that with dry snow, we're going to have high backscatter, and with wet snow, we're going to have lower backscatter, we can look at a single point and see that whenever the water starts to get wet, in this conceptual diagram, you'll see backscatter hits its minimum because the most amount of water is in the snowpack. So this is going to help us delineate between different snowmelt phases. We're primarily interested in snowmelt runoff onset, which is, again, when the snowpack has warmed and any additional energy will go into melting the snow, so water leaving the snowpack. So we're going to be using this method to map globally runoff onset. And so just as a preliminary study, we looked at some of the stratovolcanoes in the Cascade Range because they have broad range of elevation distributed across 10 degrees of latitude, and their conical shape makes it easier to study things like aspect, so like what side of the mountain that you're on, and elevation, and how those control snowmelt timing. Oh. There are some additional reasons too. Okay, so based on our conceptual diagram, we formed a method. And in this method, we prepare a time series stack of these Sentinel-1 images and locate the backscatter minima at each pixel. So we start with all these different like relative orbits, so just different viewing geometries. And each one of these orbits is a different outlined color. So all of the things in green, all the images in green are taken from like the same spot in space. And then we build a backscatter time series for each pixel and estimate the timing of the backscatter minima of each orbit. And that's represented by those dashed vertical lines. And then from those dashed vertical lines, we take the median of those dates, and that corresponds to April 25th, for example. And when we combine the estimates of different orbits, that helps us increase our accuracy as well as our temporal resolution because each one of these images is spaced like 6 days apart. So if you have 4 different viewing geometries, you're effectively increasing your temporal resolution. So then that helps us create this runoff onset map that you might see a couple of in this talk. And it's basically showing for each pixel when did runoff onset occur. So as expected, we see the lower values corresponding to runoff onset in April at the lower elevations, so those darker blues. And higher values corresponding to runoff onset in June and July at the top of Mount Rainier. So to recap, we build a time series of Sentinel-1 images, find the date where each pixel reaches its backscatter minimum, and then we create these maps that have the timing of the backscatter minimum. So let's just take a quick look at some of these results for Mount Rainier. So the top row here shows the annual runoff onset maps from 2015 to 2022. And you can see this characteristic elevation gradient that is maintained in every year. So the lower elevations are going to be melting earlier and the higher elevations later. And from these 8 annual maps, we can calculate an 8-year median. And this represents the typical runoff onset timing. It reduces the influence of like anomalous years. And then we can calculate how each year deviates from this median, creating these annual anomaly maps. So blue here indicates later melt relative to the median, and red indicates melt earlier than the median. And you might notice that 2015 stands out dramatically, and almost the entire mountain is showing 25-day early melt. And that coincides with the 2015 snow drought. If you were around for that, we had a very small snowpack, and it melted earlier in the year. Finally, we can also show this 8-year median absolute deviation map. And this is basically just showing where is there like greatest variability in snowmelt runoff onset date, and where is it higher. So the whiter values are showing where there's lower variability, so like these mid elevations, and then like the lower elevations are showing higher interannual variation. So each year, you're going to have a more variable runoff timing. So we took the median map for all 10 of these stratovolcanoes that we sampled, and we threw these, so you can actually see here in this inset here where each of these is located. But this plot is showing elevation on the y-axis and then day of year on the x-axis. So basically these curves, each curve represents one of the stratovolcanoes, and you can see that as we go up in elevation, the melt happens later in the year. And you can notice they all have like similar slopes. So we found that for every 100 meters of elevation gain, the observed median delay in runoff onset was 4.9 days later. And the general trend of melt later at higher elevations is relatively intuitive, but exact like quantification high resolution is something that we have at this point. We can also show, or actually we'll just skip here to a quick summary. So we developed and validated a scalable SAR method to map runoff onset, and we quantified the spatial and interannual variability across the Cascade Range stratovolcanoes, but this was only for one small area. And this work was published in Geophysical Research Letters, if you want to check out the methodology there. But to understand snowmelt patterns beyond these regional studies that all use different methodologies, we need more systematic observations. So this requires a consistent methodology, high-resolution data that can capture terrain complexity, has global coverage, and multi-year records. And this is something that we don't have right now. But for populations dependent on snowmelt water resources, we need to scale up our methods to answer some important questions. So I put some of them here that we're going to try and answer at the later part of today's talk. What are the topographic controls on snowmelt runoff onset, and how do those vary globally? Where is interannual variability highest? And which mountain ranges are most vulnerable to climate warming? So this data set, if we could create it, could be incredibly useful for us and the cryosphere, hydrology, and climate communities, but building it would be a large challenge. So because the building this was not straightforward, there were a lot of lessons learned over the years, and those are some of the things that we're hoping to share today. So the raw input data, the Sentinel-1 SAR imagery is over 100 terabytes. So really, really large data sets we're talking about here. So that's going to rule out like downloading any of these to like your local computer to work with. Other issues deal with like compute. There you can download locally if you want for like 1 or 2 images, but infeasible elsewhere, and traditional HPC, like high-powered computing, is limited by access and customizability. And there are newer, like cloud native frameworks that reduce barrier to entry for cloud computing, like services like Coiled. But you still have to, pay for all of these services, and they require careful orchestration. Other concerns are memory at global scale. If you've ever tried to, accidentally load some like really, really large data set in your computer and your computer crashes, that's something that we have to deal with when working with large data sets. And on top of that, traditional pipelines tend to be sequential. So even if you are, distributed, you are still doing things like relatively sequentially. So you're doing like one tile at a time, one small region at a time. Another concern is fault tolerance. If you're trying to create these like really large data sets, you want to be able to keep track of if you're accidentally writing just like garbage data to one area, or if there's a failure in the pipeline, not just thinking, oh, well, I didn't see any errors at the end, so I think everything's fine. So that's another concern that we have. But each challenge has a matched solution. So for the really large input data problem, we're getting data, we stream data from Microsoft Planetary Computer. So there's no downloading that happens to like our local devices. We use ZAR data format, and it has a chunked format. So it means that like reading one tile is not going to touch the rest of the arrays. So we can really just like query small areas at a time. For compute, we use GitHub Actions, and this is a free, massively parallel continuous integration system. It's kind of like its main intent. So like if you're building a software package on GitHub, for example, you might use Actions to like run tests when you push things. But you can also use this for scientific workflows. And people like Valentina, Quinn, and Scott, who are in the audience today, could talk to you more about that. They have some really great tutorials that I took inspiration from. So the key insight here that makes this parallelism possible is this idea of embarrassingly parallel processing, basically meaning that if I'm trying to process the Cascade Range, for example, I really don't need to know what's going on in Europe. Right? So we can just look at a time series at a small spatial chunk and not have to worry about other parts of the globe. With those, as well as some other tools like Ice Chunk, which is a way of interacting with ZAR data that basically turns these ZAR stores into like GitHub repositories where you can commit whenever you're pushing data. That's going to help us realize, what chunks are we actually writing to, and it helps us roll back any changes that we make that might be like corrupting the data set, for example. So putting all of these together to create, one workflow that we can use as a template here and for other folks, we can first create an empty template global ZAR store with Ice Chunk. And so only the tile grid metadata is going to be written at this point. So we create this grid, processing grid, made up of a bunch of tiles, and then we just write it to basically just an empty store that's going to have like the coordinates and such, but there is no like data really written to it. And then what we can do is run some process all tiles GitHub action that basically spins up some runners, one for each of the unprocessed tiles. And so each runner is going to run its own like identical processing pipeline, but only for its own respective tile. And it's going to query data from Microsoft Planetary Computer, going to do its computations, create its output. And then after the processing is complete, each runner is going to write to the global czar store. So it was once empty, but you'll continually build up your data set over time. And if there are any failures along the way, you can just rerun this one GitHub action, and eventually all your tiles will fill up. So here's an example. If we were actually running the pipeline, we create the tile scheme and we write it to just this empty store. You can see compute false, so it's not really like sending any computed data. Then another way we can, reduce the actual processing time. We don't need to, process over the ocean if we're not interested in the ocean. So we can just look at land tiles specifically. And then we can start our processing. So we go to our actions tab in our GitHub repository, and we've created these actions where we can process all tiles, and it'll basically run this process tile GitHub action for all the tiles that haven't been processed yet. And you can see on that right plot that right now there's one tile process, what it might look like throughout the processing time, which is around 40 minutes for one of these example data sets. You can see that maybe one of the actions might fail for some reason or another, and you can just rerun it, and then all tiles will be processed in the end. And that's what we use to create this really large global snowmelt runoff onset data set. So here is the result. We'll kind of jump back into a bit of the science for now. This is showing the 10-year median runoff onset across all seasonal snow, or almost all seasonal snow on Earth, at 80 meters resolution. So this is around 43.7 million square kilometers. So it's a really, really large data set, especially since you're at 80 meters. So you'll notice that since the northern and southern hemisphere experience opposite seasons, that color bar there has the southern hemisphere color bar on the bottom. But in the northern hemisphere, at least, you can see progression of early melt at lower latitudes and elevations in January and February, to later melt at higher latitudes and elevations in May and June. And in the southern hemisphere, you see that reversed. And we can zoom in to really appreciate the scale of this data set. So right now we're zooming into Washington State. You can see the Olympic Peninsula there. And we'll zoom into the Cascades because that's kind of where we started all of this work. And you can keep progressively zooming in. And right here, we're looking at Glacier Peak. And you can really see what 80 meters spatial resolution looks like, and appreciate that the processing pipeline is one that has to deal with some really, really large number of pixels. But this type of resolution is important for our analyses because we're interested in the different controls of runoff onset timing. And that's something that's really hard to do when you have very, very coarse data and you can't look at like specific small watersheds, for example. So to put the spatial resolution in context, here we're comparing to passive microwave remote sensing, and this was previously the best option for large-scale melt detection. So we're looking at the Alaska Range here, and on this top center plot is a specially downscaled passive microwave product that has 6.25 meter resolution, which is actually better than like the usual 25-kilometer product. But you can see that there's a lack of like variability in melt timing with elevation where the mountains are. But our 80-meter product is able to capture those variations, as you can see in the center bottom plot. We also show the difference in the top right. And what's pretty striking from that is we're detecting melt, 75 days later at these higher elevations, really showing that like you need this higher spatial resolution in order to get the full picture of melt in the mountains. So this comparison is actually generous just because we're using like a specially downscaled product. But if you're working globally, you'd be having to deal with 25 kilometer resolution, so even worse than this. So basically the 80-meter product in that way represents like a 300-fold improvement in spatial resolution. So just to summarize the data set that we were able to create, this is the first global high resolution runoff onset data set that we know of. And we had to use 100 terabytes of input data, but the stats are 80-meter spatial resolution, 9-day average temporal resolution, and almost all snow, seasonal snow on Earth is covered. If you want to learn more, including details on like validation and performance, you can check out our preprint to Earth system science data, as well as our Zenodo data repository that has even more details. So now let's actually apply these data sets to answer some of those questions that we were asking in the beginning. So we were interested in the different controls on runoff onset timing and what mountain ranges might be most vulnerable to climate warming. So we're going to be looking at things like latitude, elevation, aspect, and spring temperatures. So here's what it looks like to zoom into some of these key mountain regions. You can see that, similar to the global maps, at the higher elevations, you have runoff onset happening later in the year, but you get a little bit more fidelity in some of these zoomed in maps. But to understand this more in more of like a quantified way, we can aggregate into latitude bins. So for each of the set of continents shown on the left, we have these corresponding plots with latitude on the y-axis and elevation on the x-axis. And we observe gradients, latitudinal gradients below like 5 days for every degree of latitude in Asia and Europe, above 55 degrees north, indicating rapid runoff onset above this latitude. There are some other interesting things here and there that have to do with some regions that, for example, the Andes, where snowmelt runoff onset timing is very, very different depending on the year that you look at it. There's this huge interannual variability in melt. That has to do with things like just the large interannual variability in when there's actually snow there in the first place. That's something that it's not as easy as we get to experience in the most places in the northern hemisphere, where snow just accumulates in the winter and melts in the spring. Lots to talk about at the global scale. But I think for time's sake, we're going to start looking at some aggregations. The first of which is looking at runoff onset delay with elevation gain. So similar to what we did with the Cascade Range, we can look at the different delays in runoff onset per 100 meters of increase in elevation. And you can see that there's, similar to what we found in the Cascade Range, median runoff onset delay of 3.5 days per 100 meters of elevation gain. And we noticed that in the polar latitude ranges, with a little relief, there's even weaker delays. So in the interest of time, I'm going to skip past this slide, but basically what we were going to be looking at is the different different sides of the mountain ranges and what sides might melt first. Some just key takeaways from this was that these differences, for the most part, follow these north-south orientations, as you'd expect. In the northern hemisphere, the south sides of the mountains would melt first. But there were some key deviations that, if you want to talk about, we could discuss. So we looked at Mount Rainier and these anomaly maps. to see each year how did the melt timing compare to the median. And we applied this globally. And we can go through most of these relatively quickly. There's so much information in here that it's really hard to talk about. But maybe some of the key highlights is for the Western US, you can see widespread early melt of 20 to 40 days, likely related to the snow drought in 2015. Skip through most of these years, and then some more interesting things happen again in 2022, widespread early melt of 15 to 30 days in high mountain Asia. And that's likely related to this massive heat wave in high mountain Asia, which drastically reduced snow depths and also had some record heat. And these were also observed in other studies as well. 2023, we saw really late snow melt in California, which lines up with the what's called the snow deluge. So basically lots and lots of snow in the Sierras. Oops. And then in Europe in 2024, we see really early melt, and especially at the lower elevations, over 30 days in a lot of places. And that also coincides with the hottest March on record ever for this region. So we can point to these well-documented events that explain these large anomalies, but beyond that, we can try and quantify the relationships a little bit more systematically. Oops. So in order to systematically evaluate these variables, we needed to look at some climate reanalysis data sets. And long story short is we used the average 2-meter air temperature, spring average from the ERA 5 land data set. And we use that in this analysis here. So we're looking at the Sierra Nevada mountain range, and you're looking at those anomaly maps once again. So you can see early melt in 2015. And we compare this to the spring 2-meter air temperature anomalies as well. And you see some interesting patterns between these where in the 2015, we saw a mean anomaly of 1.5 degrees C warmer temperatures. And that also coincided with really early melt. So you can basically draw a line through some of these data points in order to get some sort of spring temperature sensitivity. So here, each point represents 1 year, and you can fit a line using like linear regression or a more robust method like SendSlope. And you see these really high correlations of 0.88 and a slope of 13.3, meaning that for every degree warmer spring air temperatures, you see a shift of 13.3 days earlier melt. And we did this globally. So we show this here, the slopes on this plot. So the darker reds are going to be these like higher sensitive areas. So the Sierra Nevada was one of the highest. And for the Western North America ranges, we see strong sensitivity, across the board. And as we go to the more northern latitudes, that seems to peel off a bit. And we were able to do this for 150 different mountain ranges, lots of data to look at. So I'll just tell you the takeaways. In general, the sensitivity was in between 5 and 13 days earlier per 1 degree C warmer temperatures. And the temperature influence was definitely a lot weaker in the polar ranges. A lot of them didn't even show correlation at all. And so this analysis would be helpful for us because it can help show which regions might be more sensitive to climate warming. So with different projections of climate warming, you can look at like an area like the Sierra Nevada, for example, and say, okay, if we're expecting temperatures to be 1 degree C warmer, next year or, within some amount of years, we can try and guesstimate when how that might affect snowmelt timing. Again, this is like a very rough estimation, so I wouldn't, go around like using this, but more of like a back of the napkin understanding of how will snowmelt timing shift with increasing temperatures. But more than anything else, this framework is going to enable these comparative vulnerability assessments for different mountain ranges. That's stuff that we're still working on. So just a summary of all of this work here. We were able to look at 150 major mountain ranges, and we were able to document the different topographic controls for each of these. We're able to look at some of the runoff onset timing anomalies between different mountain ranges. And we were able to establish some empirical understanding of sensitivity to air temperature. So I'll just put some of the key takeaways here. We already mentioned most of these, but the last one is this idea of a template GitHub repository that lets you run this sort of analysis where you break the globe into a bunch of tiles, and then you get to use the GitHub Actions workflows in order to process these really large scale data sets. So I'll leave that here. There's a QR code to go to this repository and some like interactive maps. I was going to try, but honestly, I feel like I don't know, live demos always work the best. But yeah, please give this a go. Use this as a template as much as, as like a pipeline, and, leave feedback and issues as they come up, because it's not necessarily the best way to do it, but the way that worked best for us. So thank you for your time. Feel free to check this out. And yeah, if there's any questions.